Got a question here that involves a couple of parametric equations. Now, if you're used to, in physics, oscilloscopes and displaying waveforms on some sort of screen, you can think of this guy as controlling the x dot. In other words, what the curve does horizontally. And this guy is what the curve does vertically. Mix them together in an oscilloscope and you will get some sort of shape on that scope. Still, we've got some maths to do. They're both trig expressions, so you can see, and we've got a limit of t from 0 to pi, so slap that calculator straight into radians if we need it. Find an expression for dy dx in terms of t. Well, we can use the chain rule. Well, out of these guys, we can get dx dt by differentiating, and similarly dy dt. You can see that one of these things matches completely, but this is just the upside down version of what we require here. So let's differentiate these two terms. This is quite a simple differential. The differential of cos is negative sine, so this turns into negative 2 sine t. The differential of this function, we have to use the chain rule again, because we will need to differentiate 2t separately from cos 2t. So this is going to become 2 root 3 sine 2t, but remember, we've produced a negative sign as well. If you didn't quite get that, look back at more examples about the chain rule, and you'll see how to produce that answer. So we can assemble dy dx now. Dy dx is equal to dy dt, which is this result, which is negative 2 root 3 sine 2t, divided by, I say divided by, yes, we're multiplying by dt dx, but we've got dx dt. So effectively we're dividing by negative 2 sine t. The negatives disappear and the 2's disappear. And we simplify to the root of 3 sine 2t divided by sine t. And that should be the answer to part A. I always think it's all very well writing this down, but what have we actually done? We've actually found the gradient function of the curve C. In other words, we know the gradient at every point on curve C, provided we know the value of t. With that knowledge, let's have a look at part B. We're now told that P lies on C, and we've got a value for t. I think it always helps to visualize these things. Let's say the curve does that, and this is the point P. Now they're saying a line L is normal to P, so the gradient at the point P looks a bit like that, and the normal to P something like that, and they're calling this the line L, and we're asked to find the equation for the line L. I'll just indicate that the value of t at that point is 2 pi by 3. How do we get to the line L? Well, we know the gradient at P, so let's first of all get that value, because once we've got that value, we know that the negative reciprocal of that value of gradient will give us line L. So gradient of C at P is equal to the root of 3 sine 4 pi by 3 divided by sine 2 pi by 3. Just a reminder what sine gets up to. That's pi radians, this is 2 pi radians. Pi by 3 and 2 pi by 3. This in old money is 60 degrees. And this is 120 degrees. And they both have the value of root 3 over 2. So substituting those values in either from a calculator or from your memory of what the sine wave gets up to, we get this is equal to the root of 3 sine 4 pi by 3. Well, 4 pi by 3 will be double this value, so it will be root 3 over 2, but it'll be negative root 3 over 2. So this is root 3 over 2, but we've got a negative sign. Then that's divided by the sine of 2 pi by 3, which is root 3 over 2. Now, tidying all that mess up, we get, well, the root 3 times root 3 will be just simply 3 over 2. So this is negative 3 over 2 multiplied by the upside down version of this guy, which is 2 over root 3. The 2's cancel, and we're left with 3 is root 3 times root 3. So you imagine one of those cancelling, and I get that the gradient is negative root 3. So that means the gradient of the dotted line here is negative root 3. So yes, my diagram is hugely wrong, but it served a purpose. So I've created a bit of space, and let's take that value for the gradient at point P of the curve C. We now know that the gradient of L, which is normal to the curve, will be the negative reciprocal of this. So now we're dealing with line L. Line L, its gradient is equal to the negative reciprocal of this, which will be positive 1 over the root of 3. And we know that P lies on it. The coordinates of P can be got to by looking at the parametric equations of C, because they apply at that point P, and just substitute in 2 pi over root 3 into both of these values, and we'll get x and y coordinates. So P is at x equals 2 cos t, well, let's just write all these down, 2 cos 2 pi by 3, and y is equal to the root of 3 multiplied by cos 4 pi by 3. So working these values out, yes, we can put it into a calculator, but if you imagine the cos graph doing what it does and coming down here, crossing down, we're below the axis, and in fact the value of cos 2 pi by 3 is negative 1/2. So our value for x here is negative 1. The 2's cancelling. Similarly, cos 4 pi by 3 is also negative 1/2, and we get y is equal to the root of 3 over 2, but we're negative. So we now know the coordinates of P in terms of x and y. To find the equation of line L, I like to use the definition of the gradient of a line, which is equal to rise over run, and the rise can be expressed as y minus y1, which is a coordinate point, and x minus x1. So if I now just put in our y coordinate here and our x coordinate here and our gradient here, we've done it. So therefore, the gradient, which is 1 over the root of 3, is equal to y minus the coordinate, so this is going to be plus the root of 3 over 2, all divided by x minus the coordinate, so this is going to be x plus 1. So multiplying across, I get x plus 1 divided by the root of 3 is equal to y plus the root of 3 over 2. And you can see we're approaching our goal quite well. What have they done? Well, they've got a y here multiplied by 2 root 3. So we're multiplying everything by 2 root 3, the denominators. So on this side, the root of 3 disappears and both of these terms get multiplied by 2. So I get 2x plus 2 is equal to, the y gets multiplied by both of the terms, so this is 2 root 3 y, and this just by root 3. So this will be simply root 3 times root 3 plus 3. So again, running out of space, we get, just push it the way they want. They've pushed everything onto the left-hand side. 2x is where it should be. So we have to move the 2 root 3y, and this becomes negative 2 root 3y. The 3 jumps side, becomes negative. Negative 3 plus 2, negative 1 equals 0. And that was the answer they require. And that's the end of part B. So let's have a look at part C. They now tell us that the line L intersects with curve C again at a new point Q, and we're asked to find the coordinates of Q. So if this line L touches C again, there must be another value of t which would pop out of a substitution. If I shove in x is equal to 2 cos t and y is equal to root 3 cos 2t into our equation, yes, we're going to pop out the value of t that we know and love, which is 2 pi by 3 where the two lines meet, but there must be another solution. And that solution will be the t value of the coordinate point Q. So let's try it. So I'm substituting x is equal to 2 cos t and y is equal to the root of 3 cos 2t. And remember, t is limited from 0 up to pi radians. And that might stop us finding endless solutions of the intersections. Okay, putting these two values now into line L. So this will be 4 cos t minus 2 root 3 cos 2t minus 1, and that equals 0. Tidying up, we get 4 cos t minus root 3 times root 3 is 3 multiplied by the 2, so this is 6 cos 2t minus 1 equals 0. Now we can use a trig identity to get rid of cos 2t and get it back into terms of just cos t. And that identity is that cos 2t is equal to 2 cos squared t minus 1. If we now substitute that back into what we've got so far, we will get a quadratic in cos t. Let's do it. So I therefore get 4 cos t minus 6 lots of this, which is 12 cos squared t plus 6 minus 1 equals 0. So therefore, making the 12 cos squared t term positive, I get 12 cos squared t joined by a negative 4 cos t minus 5 equals 0. Now if you imagine cos t equals, let's say, a, we've got a quadratic in a. Given that one of the solutions we're expecting to find is 2 pi by 3, I think it will be hopeless to try to guess the solutions of this quadratic equation, so I'm going to go straight into the quadratic formula, where we've got a is equal to 12, b is equal to negative 4, and c is equal to negative 5. There's the arithmetic of using the quadratic formula. You could, of course, put that into a calculator and get these results back. So we've got the fact that cos, remember it's cos t equals these results, is equal to 5 over 6, or cos t equals negative a half. Well, cos t equaling a negative a half is the solution which ends up at the point P, where t is equal to 2 pi by 3. So this solution here must lead to the point Q. This is the point P, and this is the point Q. So to find the x and y coordinates of this point, we have to use our parametric equations here to convert our value of cos t back to x's and y's, and we get that x is equal to 2 times this, which is 10 over 6, or 5 over 3, and y is equal to, and we've got to use this identity again because we've only got cos t. So y is equal to 2 cos squared t, which is 25 over 36 minus 1, all multiplied by the root of 3. And if you work that out, the 2 will go into the 36 18 times, and we get 7 over 18 multiplied by the root of 3. And those are the two coordinates of the point Q. And that's your answer.